All right, today we're diving into something truly incredible, a tool that is completely changing the game when it comes to diagnosing brain tumors. This is a story about data, about brilliant minds working together across the globe, and about a huge leap forward in medical precision. So let's get right into it.
Now, you might think this is a simple question, right? But the answer has gotten so much more complex and way more precise. For the longest time, the answer was based on what a doctor could see under a microscope. But what if the tumor could tell us its own story in its own language?
You see, for decades, figuring out exactly what kind of brain tumor someone had was like trying to solve a giant, complicated puzzle. So many different tumors can look almost identical, which makes choosing the right treatment incredibly challenging. But that's all starting to change. Big time. So here's the fundamental shift. The old way, the classical approach, using histology, is all about what a tumor looks like. And don't get me wrong, it's super useful, but it has a built-in problem. It can be subjective. You could have two world-class pathologists look at the same slide and come to slightly different conclusions. The new molecular approach, though, it's like a DNA test for the tumor itself. It's based on cold, hard data, objective, data-driven, and you get the same result every single time. We're moving from just looking at a tumor's appearance to understanding its fundamental identity. So how exactly do we read that identity? How do we find that unique fingerprint? Well, the secret isn't actually in the DNA sequence itself, but in these little chemical tags on the DNA. It's a fascinating bit of biology. Let's break it down. The key to all of this is something called DNA methylation. Okay, think of it like this. Your DNA is the master blueprint for your entire body, right? Well, methylation marks are like tiny little sticky notes or highlighters on that blueprint. They don't change the words, but they tell each cell which parts of the plan to read and which to ignore. This creates a unique pattern for every cell type, essentially a biological ID card that says, I'm a brain cell or I'm a skin cell, and shows exactly where it came from. And it turns out this system is the absolute perfect marker for tumors. Why? Well, for one, these patterns tell us the tumor's original cell type, where it all started. Plus, these patterns are incredibly stable and reliable, giving us a unique, undeniable fingerprint for each and every tumor. They even track how the tumor changes as it grows. It's basically a goldmine of diagnostic information all packed into one place. So, a team of brilliant scientists at Heidelberg University realized they could use machine learning to read and interpret these millions of little sticky notes. And that's how this incredibly powerful tool was born. They called it a classifier. It's basically a super smart program that can sort through all these complex patterns and identify the tumor with amazing accuracy. And it didn't stay in their lab. It became a massive global resource. The whole journey really kicked off in 2016 with version 11, but the real game changer was when they launched a web platform. This let doctors and scientists from all over the world upload tumor data for analysis, and the response was huge. By 2024, they'd analyzed over 160,000 tumor profiles. All that data allowed them to spot brand new patterns and even identify tumor types that nobody knew existed before. And all of that work led to the super upgrade we have today, version 12.8.
And listen, when I say this was a massive upgrade, I really mean it. This isn't just a fresh coat of paint or a minor tweak. No, this is a quantum leap forward in the level of detail and precision we can get. Just look at the difference here. The scale of this improvement is staggering. Version 11 was trained on around 2,800 samples, which was amazing for its time. But version 12.8, it was trained on nearly 7,500. But the most important number on this chart is the one on the far right, the number of tumor classes it can recognize. So, the original classifier could distinguish between 91 different types of central nervous system tumors, an absolutely incredible achievement back then. And the new version? 184. That is more than double the diagnostic power. It can now tell the difference between tiny subtypes of tumors that used to just be lumped together. And this is huge for patients, because these different subtypes can respond in completely different ways to treatment. So how on earth did they do it? Well, this chart tells the story beautifully. It wasn't just one team in a lab. While the original data and all those user submissions were critical, a whopping 70% of the new data came from collaborations with institutions and new cases from around the world. It just goes to show the unbelievable power of global scientific teamwork. And it's not just bigger, it's also incredibly accurate. We're talking 95% accuracy, even at the most detailed, granular level of classification. On top of that, it gives doctors a confidence score for every diagnosis so they know exactly how certain the result is. This gives them a level of confidence they've just never had before.
Okay, so the science is clearly amazing, but let's bring this back down to earth. What does all this actually mean for doctors and, most importantly, for patients in the real world?
Well, for starters, this isn't just some fancy research tool anymore. It's quickly becoming the new standard of care. The World Health Organization, along with other major medical groups, now recommend it as essential for diagnosing certain tumors. And why is that? Because getting the diagnosis exactly right is the first, most crucial step to creating a personalized treatment plan, one that's tailored to the unique biology of a patient's tumor. That's what gives them the best possible shot at a good outcome.
And the actual process in the clinic is pretty straightforward. First, a sample of the tumor is taken during a biopsy or surgery. Then, in a lab, its unique DNA methylation profile is generated. That data is fed into the V12.8 classifier, and in a short amount of time, the doctor gets back a super precise, data-driven diagnosis, complete with that all-important confidence score.
And here's what's so incredibly powerful. This one single test gives you a whole suite of answers. It doesn't just name the tumor. It also reveals critical information about its genetics and gives clues about how it's likely to behave in the future. Things that used to take multiple, separate, and expensive tests are now all wrapped up in one comprehensive analysis.
The Heidelberg classifier is just a stunning example of what can happen when you combine big data, brilliant machine learning, and a spirit of global collaboration. It really just leaves us with one massive, exciting question to chew on. What other areas of medicine are on the verge of a similar, data-driven transformation?